Mhm. Hello. See people coming on. Exciting. Welcome, everyone. My name is Verena, and I'm the teacher at Earth Building School. And we're kicking off day 3 of the Design Your First Earthen Tiny Home challenge, which, I am really, really enjoying seeing people's floor plans coming in. We started a couple of days ago, so if anyone watching here is new to the challenge, welcome to you too. And the replays are up in our group, and if you signed up via our link to our page, so the challenge earthbuilding.academy, you will also receive the link to a recap page. So the recap page is for anyone who feels like they're falling behind a little bit, or they would like to see everything in one place to be able to go through the materials. And it will also be available after the challenge for a little while. So don't fret if you haven't quite been able to do all the things that we have covered so far. It's totally fine. And you will still be able to follow today's training, even if you haven't done the previous trainings. But if you want to develop your design, I would suggest that you go through the material in chronological order, because it sort of builds up one on the other. And it's also kind of standalone. So all you need for today, really, if you have been working on your floor plans already and you want to follow along, the only thing you really need at this point is the dimensions. So the length and the width of the room, or you can just sit back and watch me present a couple of examples, and then go to your design and start fine-tuning what you've learned. So just to orient you to how I see the session roll today, I've prepared a presentation with slides and photos and so forth, so that we can look at some concepts that regard structural considerations. So today we're talking about structure, foundations, roof structure, and so forth. And then we'll move into worked examples. So I'll be sketching again and showing you 3 examples of roof structures. So the roof structure is what I invite you into looking at in more detail today. The whole topic of structure is big. Obviously, everything in your tiny house to a certain degree is structure, because you're looking at a small building. So your walls are structured, the roof is structured, the foundations are structured. There's pretty much no non-structural elements in your building because it is very small. So structure means any part of the building that takes loads. So to give you the comparison to something that is non-structural would be a division wall, a wall that doesn't take loads, that just gives you privacy. And in bigger buildings, there's always a combination of structural elements and non-structural elements. But in a small building, everything is structural. So I hope that sort of clarifies the terms a little bit for you. So I am actually curious, before we start, just to welcome everyone, say hi, maybe tell me where you're watching from, and also welcome to people that are watching the replay. So if you're watching the replay, maybe just give me a little comment in the comment section. I'm watching the replay from this and this place, and that gives me joy because it lets me feel the community a little bit, and it also lets me connect into how far this is reaching. And just wanting to say, I am teaching to the New Zealand Earth Building Standards and the New Zealand Timber Frame Standards, but both these standards are internationally applicable. So they're definitely relevant, and they're free for download. So wherever you are, I'm really inviting you into having a look at these 2 standards and having a go. So yes, France, USA, wonderful. Thank you. Okay, so let's start with the presentation. Today we're talking about structure. That's already understood. And I'm always having to start with this little disclaimer at the start because, I am teaching online. I'm using uh, some teaching materials that are, from official sources, and I am inviting people into designing buildings. So if you're not based in Aotearoa, New Zealand, this is not so relevant for you, but for anyone watching from this place where I'm based, there's a scheme called the Licensed Building Practitioner Scheme, which licenses designers. And I'm not a licensed building practitioner. I'm an earth building artisan. So I have 30 plus years of building experience, practical. I have also a design background from my country of origin, Switzerland. But I am not designing in New Zealand and I'm not licensed to design. And also, I haven't been really able to get the legislator to assess my work because it is kind of an alternative. So I have an exemption. And I still feel that I have a lot to share, practical knowledge, and just based on working with self builders and designing my own building, my own home, and also buildings for other people before the scheme came in with a really practical lens, really wanting to empower people to not be afraid to start designing themselves and also building themselves. So obviously, that being said, I'm not liable for anything you design or build. And I really encourage you, wherever you are, to check your legal requirements in case you need to get a building consent or to make a decision whether or not you want to apply for that. Regardless of that decision, really, really encouraging you to build safe buildings, to design safe buildings. So you're designing to code regardless of whether you apply for a building consent or not. So it's very important to us as a school to promote safe building practices for any location. So here in Aotearoa, New Zealand, we deal with quite harsh environmental conditions, so earthquake and strong winds, and it is important that we keep buildings safe. But that applies to everywhere on the planet, and especially with changing climate, the wind has to be taken into account a lot. And also just to manage expectations, what we can cover in these 5 days is sort of basic design. It's not a how-to tutorial of how to put things together. That's something we cover in our paid 3-month program and the year-long mentorship. Takes a little bit more, to look at really individual situations and come up with really good solutions. But I'm very confident, that we can talk about a lot of things in these 5 days. And if you're engaging in the group, pick my brains. I'm very happy to answer questions. And we're starting small. So I have invited everyone into sticking to the 10 square meters because that will allow us to keep it digestible enough and learn the design principles, learn the constructive principles, and then you can take that and scale if you want to bigger buildings. And also, if you're thinking about building down the track, the 10 square meter building is totally achievable. It could even be done without a plan, but it is much better to do it with a plan. And another reason, which applies more to Aotearoa, New Zealand, is that the 10 square meter cabins don't require building consents or LBP supervision for both construction techniques that I have presented in day one. So some of you will be looking at earth timber hybrids, so more like a timber frame construction, following the timber frame standards, and then with earthen components, so light earth infill or a bottom dope panel or stuff like that. And quite a few of you are actually looking at solid earth construction. And you're choosing one or the other to go through the design challenge, but you can always repeat the whole process with the other type of construction and just compare notes. So really encouraging you to have an open mind. Sometimes you know exactly what you want to do and you just want information to be able to implement that. Some of you, you're just coming as newbies and you might be drawn towards a technique, but there's actually quite a few ways of looking at that decision, which technique to choose, be it cost or available resources, your logistics, your skills, and so forth. So really inviting you into watching that presentation of day one and making a decision that really suits your specific needs. So today we're going to look at the structure. So we'll start bottom up, foundations and walls. We'll only cover that in the lecture a little bit, to get your thoughts going around that. And then we'll look at roofs. And, I want to show you this. It's a little bit small on screen. You don't need to read all the things. They'll be highlighted a little bit later on. But this is a diagram that we have been using for years and years, and it's not 100% aligned with the current earth building standard anymore, but it shows the principles. And I'm starting with the solid earth construction now to show you how a solid load-bearing earth wall is put together. And on this image, it's mud bricks, but it could also be cob. It's the same for cob. It's the same for rammed earth. So you have a nice and chunky wall. The minimum thickness for a load-bearing earth wall is 280 millimeters. And you see the wall is standing on the foundation here. The foundation has a couple of purposes. So the foundation can be in contact with moisture. It is strong, so it can take the weight of the walls, and the solid earth walls have substantial weight, even if you go to low density adobe. So you need to have good foundations. There's always that saying, an earth building needs good boots and a good head. So the boots are the foundation. The foundation transfers the weight of the building into the ground, and it has to stand on solid ground. So there was a question in the group, what about if my site has got expansive soils? Like, you have to be sure that if you're building with solid earth construction, that you have good ground. So good, strong ground. And sometimes that has to be assessed by an engineer, or you can ask your digger operator, what they see when they dig the building platform. You can do a thing called a penetrometer test, where you see how easy it is to get a rod into the soil. And there's different ways of just assessing whether your soil is strong enough. You have to really make sure that foundation doesn't slump under the weight. The foundation also brings the whole building out of the ground so that it is above the moisture of the environment, and also splash back from rain. So you see there is this minimum height of the finished ground on the outside. And also the way it's shaped is there's a fall away from the foundation. So you're really wanting to direct water away from your building. So that's the foundation. Very important is that when you're having a foundation, usually often you're using concrete, so steel reinforced concrete for that, especially in Aotearoa, New Zealand, where we have earthquake. This concrete foundation is pretty much the only thing you can do, unless you work with an engineer and they find a safe solution for a really strong foundation that uses other materials. In other countries, you can consider things like rubble trench or stone foundations. So inviting you into looking at options there. The red line that has appeared here is really, really important. It's called a damp-proof course. So any type of construction, but especially earthen construction, needs this damp-proof course, which prevents moisture from traveling up from the foundation into the mud brick wall. So concrete in particular actually attracts moisture, and it can handle it because it doesn't disintegrate in moisture, but it is a kind of a damp material. Mud when it's dry, in its dry form, is very, very dry. So it would be continuously wicking moisture out of the foundation. So that's why you have to apply this damp-proof course. And usually it is a thing like bitumen paint or something like that. Yeah, so you have this damp-proof course, which is a very important part of the foundation. Then traveling up, the structure above the foundation is your wall. So your load-bearing wall is made out of earth, either mud brick, rammed earth, cob. In seismic areas, the earth walls are reinforced with steel. So you have a vertical reinforcing bar going from the foundation all the way up through the wall, and then at the top it gets tensioned down. And it also has horizontal mesh every so often. So the reinforcing of the earth wall works in both directions, the horizontal plane and the vertical plane. And it is kind of not quite the same, but it is kind of similar in concrete construction. But in concrete construction, there's way more steel. So in your earthen walls, you typically have steel in your corners, either side of openings of windows and doors, and then every so often in a length of wall. So typically about every 1.5 meters. So not as often as in a concrete block wall, for example. And then at the top, you see there's often a piece of wood, a chunky piece of wood that then receives a washer and a nut that allows the steel to be tensioned. Because earth, similarly to concrete, actually is it's very strong on compression, so on forces pushing down, but it is not very good on tension. So a building always is under a lot of stress from different directions. So it's not just the weight of the roof sitting there, like it's also wind uplift and in an earthquake movement, which puts tension on the building, and that's why we need the steel to increase tensile strength. If you are in a country that doesn't experience earthquakes, you don't need the steel. So that's particularly important for seismic areas. So here you see highlighted that it's called a top plate. Can be timber. Sometimes that is bombing. So switching over to the foundations of timber framed buildings. So now we're talking about a timber earth hybrid, which the structural elements of the timber earth hybrids are timber. So your timber structure also requires footings. And for that, you would be looking at the timber frame standard, section 6. So you're looking at foundation and subfloor framing, and you will see there is different options for footings. So some of them are also concrete walls that are under a timber building. So you have a whole wall that is your foundation. Sometimes you have concrete piles or even timber piles, so treated timber piles. And when you're designing a small timber building, it can be like a 10 square meter building. Some people actually like the idea of being able to lift the building or drag the building out of the location it was built later on. So to have that flexibility, they don't tie, they don't anchor the whole building into the ground with a really big footing situation. They even build on skids. So just big timber bearers that are sitting on the ground that are tied down to the ground. It's also a possibility. The only thing is when you're dealing with any form of timber in ground contact, the timber has to be adequately treated. So just taking a note of that. So I'm really, when I teach, I strive to not use too much jargon, but it is nearly impossible because we have got the building jargon. So I'm just going to periodically recap a few terms. So we have talked about foundations, and sometimes they're also called footings. So that's the part of the building that goes into the ground it lets the building transmit loads into the ground, and it brings the building out of the ground. So it has to be strong and stable onto stable ground. Then we talked about the damp-proof membrane, so DPM. It's the coating that minimizes water and water vapor penetration up through the foundation and into the walls. It's the same for earthen buildings and for timber buildings. So also timber buildings, they have a damp-proof course under the bottom of the timber walls. Then we were talking yesterday about bracing already. So when you were doing your floor plans, I was talking about the stiffness and the stability of the building. That's expressed in the term bracing capacity. And it's really the strength of the building, the ability of the building to withstand forces coming in, lateral forces from earthquake, wind, and so forth. So it's how stiff the whole building is and how strong it is in relation to these elements, the wind and the earthquake. And when we're talking about the walls, there's also often the question, what about the R value? The R value is the insulation value. We talked a little bit about the difference between insulation and thermal mass in the first lecture in day 1. So really inviting you to understand this difference. R values relate to insulation. And it's really, keeping the warmth in the building, which is important, especially if you're in a temperate climate or a cold climate. And the calculation of this R value is often something that people ask about, because if you go and you just buy insulation material, you can read how much the R value is. You read that on the packet. If you're working with earthen materials, be that in solid earth construction or in an earth timber hybrid, you will be producing your own, or you will be specifying earthen mixes of a certain R value. And that R value depends on the wall thickness and the density, so how light the earthen mix is. And there is in the standards, there is a worked example, that takes you right through how you calculate that. And I'm pretty sure that I did a live stream about it, showing people how to do that. And I'm trying to locate it. It's somewhere in the group. The sad thing about Facebook is that everything disappears down the feed. So I'm trying to find that, and I'm trying to bump it again, so that if any of you is interested in how to determine the R value of your structure, you can follow that training. So that brings us to the roof. And I'm saying simple roof structures because there's some really complicated roofs. We just have to start wrapping our heads around that. So I'm just giving you a little bit of a warning. It might be a little bit brain bending, maybe a little bit dry. I'm really trying to break this down in a simple way so that you can understand it. And I'm also really acknowledging that it can be complicated, and especially if you have never really thought about a roof structure before. So it's the same thing for me teaching it. I've taught this many times, but every time I'm still like, I really want to make sure that this is conveyed in a simple enough manner. And please don't be shy asking questions in the group or even now. I'll try and go slow enough so that if there's questions, I'll have an eye on your chat and I will see this. So don't be shy asking. And if you have the floor plan, or if you have even just the outline of your cabin, I invite you to follow along and already start maybe sketching, following along the concepts of what I'm presenting, so that you maybe identify if you have questions. right now. So before we go into it more, I just wanted to show you a couple of elements of roof structures so that we have those words down. So here you see the images are out of the timber frame standard, and they just highlight the members in orange. So here we're looking at a ridge beam. So the ridge beam is if you have a roof shape that has like an apex like this, you have often a beam in the top of the apex that supports the rest of the roof members. That's a ridge beam up in the ridge. Here, down here, that's a lintel. So when you have openings, doors or windows above that opening, you always have a span of timber. Often it's mainly timber in timber construction and in earth construction that spans across the opening and then sits on either side, rests on the wall. That's called a lintel. And what the lintel does is it holds everything that is above. So here you see, there's a section of roof that needs to transfer its weight down onto the wall, but because there is an opening here, we need to transfer the weight to both sides of the window. So because of gravity, all the forces in the building, some of the forces come down, and they have to be transferred down into the foundation. So just imagine that force is flowing down, and think about where it would be flowing to. I hope this makes sense. And yes, so just wanting to go back for a moment. This is a three-dimensional depiction of two possible roof shapes. I think it is easier to read than this, which is a two-dimensional depiction. It's called a section. So this here is, imagine you're cutting through your building and you're just looking at the cut. Does this make sense? So maybe give me a one in the chat if the difference between the two-dimensional and the three-dimensional depiction makes sense, and if it's clear what you're looking at. So just imagine you're cutting through and you're looking at the building. So here you're looking at the ridge beam again. So here, you're looking at this here. It's like you're cutting here and you're just looking two-dimensionally down into the building rather than bird's eye view onto a three-dimensional thing. And I've put this in to show you a couple of different options for roof shapes. So the one on the right, bottom right, that's again, has a ridge beam, and it has got members, timber members that then transform the roof and go over to either side of the building, resting on the walls. So in this image, it is a timber wall, but it can be an earth wall. It's the same thing. The image on the left, just forget this thing, the lean-to thing, for a moment. If you look at that and you imagine that you have two walls and you have only one roof slope, so it's a monopitch roof. One side of the building is taller, the other side of the building is a little bit less tall, so that you have a fall in your roof so that the rain can flow down. This is called a monopitch roof. I'm going to show you both, like examples for a monopitch roof and examples for a roof that has like a ridge beam. So with the the ridge up here. So just keeping in mind that depending on your design, depending on whether you want to incorporate a sleeping loft and so forth, one or the other might make more sense. And just zooming in a little bit more again, just to look at structure in general. So regardless of the shape of your roof, the roof has to be really well connected to your wall. So it's important because imagine, like with wind, there's uplift. It's quite a lot of force on the top of the wall and on the roof. So this connection, the roof to wall connection, has to be really well detailed and well executed. You have, good amount of fixing, and that's also why this timber element at the top of the wall is important, because then you can tension that piece of timber down onto the wall, but also use it for fixing for your roof members and for the timber roof members to sit. And the roof has so these roof members are called rafters. So the rafters sit on here. They are additionally stiffened by what you call a structural ceiling diaphragm. So if you imagine the building, the whole building as a box, and imagine like a shoebox without a lid on, you can imagine that if you're starting to push on the sides of the box, like the top could go like this, because the bottom of the box is in the ground and often has a concrete pad, it's stiff, but the tops of the walls are not secured yet. And just having a roof up there that is not in itself braced is not enough. Like, it can move quite a lot. So you have to introduce something in the roof that also stiffens the roof, that gives bracing to the actual roof structure. And then it is like putting the lid onto the box and everything is more stable, stiffer. So your ceiling diaphragm does that. It's often made out of plywood or diagonal boards. So you need to incorporate that. That's important. And I'll show you another depiction of that in a moment. So you have the ceiling diaphragm attached to your rafters, giving stability. And then on top of the rafters, you have smaller pieces of timber going the other way that then allow you to fix your roofing material. So here in Aotearoa, New Zealand, we mainly specify lightweight roofs with corrugated iron, something that doesn't introduce a lot of weight because of earthquakes safety, because anything that is higher up in the building will move more in a shake. So this can be sheet iron. In your different countries, it could be something else. So just see what is done typically and what kind of structure is required for the type of roofing that you want to put on your building. Some of you might want to create a green roof. That's great. It has a certain structure. It introduces a lot of weight. So if you're having a green roof, you're dealing with a heavy roof, and then all the roof members have to be specified in a much stronger way so that you can make sure that it's strong enough to carry the weight. And then another couple of things to point out here that are particularly important for earthen buildings, but for any type of building actually useful, are the eaves. So roof overhang to protect the walls from rain to a certain degree, but also to allow you to play with sun angles. So to give you summer shade enough so that you don't overheat. It's very important actually for smaller buildings, because they do overheat if too much solar gain comes into the small space. And then at the end of the roof overhang, there's the gutter. So that's also important, because you want to direct water away from the front of the building. So imagine if you just have rain coming down off the roof, and then with wind it would just water blast your walls, and that's not so good. So if you have a gutter, it will just direct all the water away from that front line of the roof. So we'll just recap that for a moment. We talked about the lintels that span over the windows. We talked about the top plate, which is that timber member at the top of the wall that allows you to get a really good wall to roof connection. We talked about the diaphragm, which is the stiff element in your roof that prevents the roof from moving. The ridge beam was in the construction where the roof was like this. There's a beam here that spans between the walls and then takes all the members of the roof. The members are called rafters. So the rafters are the pieces of timber that then go from the ridge beam down to the walls and that form the shape of your roof. So when we're looking at roof structures, we're working with timber typically. So you need to look at the timber frame standards 3604. It's for free download. And I've just put this page in here because it's quite a big standard and it can get a bit overwhelming. So I just wanted to direct you to the relevant sections. And I would suggest, have a look at section 1 if you need a little bit of a recap of what we just covered, the definitions, especially the figure 1.3, to really explain to you a couple of things we'll just be going into in a moment. So the spans and the loaded dimensions. This is what I'm really trying to clarify is what that means. But if you need to recap that, go to figure 1.3. And then there's a few different tables which allow you to then size the different members of your roof. So sizing means that you can find the right size of timber so that you can start making a list of the types of timbers that you need for your building. And this is actually really important, I think, even if you build a small building, to have this down so that you then can either buy the timber or get the timber milled so that you know the quantities and you can start finding out how much that will cost and how many fixings you need and so forth. So doing this roof plan is kind of important. So you can sometimes just sort of flow through it with the rest of the building, but then when you get to the roof, at least I think it's important to plan it out properly and make sure that you have a good understanding how it all goes together. Okay, so that will bring us to the worked examples. And I'm just checking the chat in case there's any questions right now. Seems to be good. Let me just go over to my drawing tablet for a moment. It's gone asleep. So I will be drawing again, hanging over my drawing tablet over here a little bit. And I'm presenting 3 different, let me just bring that up. Yeah. I'm presenting 3 different types of roof, and hopefully that will give you something to work with and without me overloading things too much. Okay. Just making sure that you can see this. Can you give me just a 1 if it's all good? I think you will see it. Yeah, thank you. I sometimes get excited and then I launch into it. I have done live streams where there was no sound or the screen share wasn't turned on. So thank you for giving me feedback. Okay, so example. Let's go to example. No, it's not actually showing the right one. Wait a sec. This is not the right one. I want to go to example 1. Let me just stop. Wait a sec. Let me just figure this out. Yeah, that's better. Thank you for your patience. Here we go. Example 1. So I am assuming for this example that we're putting a roof onto a solid earth wall. It doesn't matter. So if you have a timber earth hybrid, it will be the same thing. The only difference is that your entire structure is built from earth, from timber. The connections will be a little bit different. Your wall thicknesses will be a little bit different. But you still have the situation where you have a top plate and then your timber roof attaches to the top of your wall. And in this example, you see, the wider walls, the wider earth walls have got some reinforcing steel. So these little dots here are reinforcing steels. But you see that they're not that often. So here, they're in the corners, and then they would be on either side of opening. So here we're looking at a situation where the door might be here, the door might be here. So there's a steel on either side, but there's not that much steel throughout. So I'm just going to remove this so that we have a clear image. So that's just a little side note to the walls. If we're thinking about building a roof onto this size building, one possible option would be to have a roof that has the shape of this mono-slope roof, So if you think about the bottom image here, the section, the section shows how the roof is sloping. It's when you're transferring this to your floor, like looking down onto the building. So the top thing is a floor plan, the bottom thing is a section. When you're transferring the concept of the section onto your floor plan, in this example, the front of the building will be the higher part of the building, the back of the building, the longer side, but the back, top of the page is the lower part of the building, and the roof flows into this direction. So I'm just going to, so this direction here is this direction here, if that makes sense. Okay, so we are in a situation where the front of the building here, so this is the front of the building here, and the back of the building here supports the roofing members. And the roof member has to span the entire length that I drew with this arrow. So it has to span all the way from here to here. And the way this is done with a monoslope roof is you don't have a ridge beam because there's no ridge. You're just building up the front with timber here to get it to be taller. And then you're working with rafters. So the rafters sit on your building in this direction. And they have a span. This is the span, They span all the way from the tall part to the less tall part without any additional support. So that's your span. So the rafter span, if you look at the dimensions of this building here, the building is 2.4 meters deep. So the rafter span is 2.4 meters. And in a situation where, how should I put this? Where, like here, if you think about it, the walls, these two walls, so the back wall here, the back and the front wall, they both equally take the weight of the roof. So the weight of the roof is divided up 50-50 between the back wall and the front wall. So the front wall takes 50% of the weight, the back wall takes 50% of the weight, and the rafters are what transfers the weight of the roof into the walls. So because it's 50-50, this is called loaded dimension. So the loaded dimension in this example is 50-50. This is the loaded dimension. The load goes onto the back wall and the loaded dimension onto the front wall. So 50% of 2.4 meters is 1.2 meters. So loaded dimension is 1.2 meters. So this is example 1. Okay. We'll just take a mental note of this for a moment, and we'll go to example 2, and that will just show you a different scenario, so a different roof shape, okay? So same building, 4.2 meters by 2.4 meters, but it has got a ridge beam and it's got like a roof that has this shape, So at the bottom again, you see a section through the building and you see the difference in roof shape. Here you see the ridge beam, and I'll just show you where the ridge beam sits in the top. So if you look down, or if you looked up into the ceiling, the ridge beam would be sitting here. I hope that makes sense. And on top of the ridge beam, you have the rafters. So these are the rafters again. The rafters now sit from the ridge beam to the back wall and from the ridge beam to the front wall. So they sit like this. Like this. And along. And in this scenario, your rafters are shorter, so they're half the length of the previous example because they're supported by the ridge beam. The ridge beam is a long beam that spans all the way from here to here, so it has a big span of 4.2 meters. So it spans 4.2 meters. The rafters have a shorter span now. They only have to span from the center of this wall here to the back, or from the center to the middle. So it's half of the 2.4 meters. So they are only 1.2 meters long. And now we're thinking about the loaded dimension, because the loaded dimension is something that we need when we look at the sizing of the timber. So if you think about the ridge beam taking some load here and the back of the wall taking some load here, half of the weight of the roof goes onto the ridge beam and half goes onto the wall. So the loaded dimension goes through here, and same thing here. Half goes this way and half goes this way. So the ridge beam, I'm just going to show you over here. The ridge beam takes this entire has this loaded dimension here, and then the rest flows here and flows here. So the ridge beam, this is the loaded dimension here, or the ridge beam. And the loaded dimension, if you think about this, it's hard. So it's 1.2 and 1.2 divided by half, so 0.6 plus 0.6. The loaded dimension is 1.2 meters again, roughly. Does that make sense? Oh, no. I want to still share it. Wait a sec. Now why it's turning itself off again. Maybe it's overloaded with thinking. Okay. I think that works now. Okay. So again, we'll take a mental note of these measurements, and then we'll go to a third example. Same floor plan again. But this time, we have a different scenario. So let's say we want to incorporate a sleeping loft. Okay, we're deciding we're having one part of the building be taller, like this, and then there's a sleeping loft in here. So in here, there's a sleeping loft. This time, you see the ridge beam is going a different way. So it's going through here. And we have rafters running this way and running this way. So you see that the ridge beam is shorter this time round. So the ridge beam is 2.4 meters long. And then some of the rafters are short and some of the rafters, so rafter A is long and rafter B is shorter. And if we look at the loaded dimension for the ridge beam, we're going to, again, half this here and half this here, and see that this here is the loaded dimension. So it's a bigger loaded dimension onto this ridge beam. So the ridge beam is 2.4 meters. Rafter A would be about 3 meters long. So 3 meters. And B is 1.2. And the loaded dimension here is 0.6 and the half of 3, so that's 1.5. So the loaded dimension would be 2.1. So I hope this makes sense. And if you get stuck when you're looking at this, just make a little sketch of how you want to have the roof, and I'll help you out. This is probably the most confusing part of the thing. Once you have it, once you understand, you need spans of your beam. If there is a beam, you need spans for your rafters. There's definitely rafters in a roof. And then you need to understand what the loaded dimension is. Once you have that down, you're off. You're all good. So with that being said, you take those measurements, the spans of the different things, and then you go into your standards. And in the standards, you look at the tables. So here I'm going to show you what I did. I just go back. So I'm going back to example 2 and 3, because the first thing we're looking at, it's just how it's presented in the standard. The first thing, or they talk about these ridge beams. If you need a ridge beam in your design, you need to know the span of the beam and the loaded dimension of the beam. So the span of the beam, remember, it was going across the long side of the building. In the middle was a long span of 4.2 meters. The loaded dimension was 1.2, so shorter. And what you do when you have this, the way you read it out of the table to size, we're doing this to understand what kind of size timber we need for this beam. First thing you do is up here, see, loaded dimension. We have 1.2, so we're in the lowest category. 1.2 is very small, so we go to the 1.8, the lowest possible, the first that sort of fits. We go into this column here, and then we look for the closest possible span. So we go down the column of the span, and you see here, like we have a span of 4.2. The closest possible is a 4.3 there. And if you look across to the left, the span 4.3 requires a timber that has 240 millimeters times 70 millimeter dimension. So that's how you size your ridge beam. So in this case, we will need 240 times 70 as a minimum size timber for it to be strong enough. And then the other thing you can do is, again, if you read across to the right into the column of the fixing type, you see it's an I. And then the I below is the explanation of how much fixing has to go into securing this to be safe. And that, will depend a little bit on your wind strength and so forth, but that's how you read it, the fixing types. So I hope that makes sense. Let's go to example 3. So example 3 was the one with the sleeping loft where the ridge beam was shorter. It was going across the narrow side of the building, and then it had the longer span for the rafters. So here you see it has got, you can't actually see it. It's cutting it off. Let me look in my example. So you have the span of the beam is 2.4 and the loaded dimension is 2.1. So again, you will go into the table. 1.8 doesn't cut it for the loaded dimension. It's too little. Go to the next one up, 2.7 ample. And then you read down the column for a loaded dimension of 2.1. And here you see 2.1 is 290 by 45. That's a possibility. So, and then you could also go, maybe I don't want, 290, because that's quite a big piece of timber. I want it to be less deep, but a little bit fatter. You could also choose something that is 190 times 70. So by reading here, you get the minimum sizes, and then you can choose, maybe something suits better in terms of dimensions and for your head clearance and so forth. So that's how you read that out of the table. You just have to have the minimum requirement, and then what you do, if it's more than minimum requirement, you're all good. So that is how you size the ridge beams. The next step, that is if you have a ridge beam. Sometimes your design doesn't have a ridge beam. So in our examples, number 1 didn't have a ridge beam. It was just spanning from one wall to the other. The other 2 examples had ridge beams, but every roof will need rafters. So the next thing is, the table 10.1. sizing the rafters. And again, that's why you need the span of the rafters. In example 1, it spanned, along the narrow side, it was a 2.4 meter span. And here you read, so span, you have options. I'll just explain this to you in a moment. So see the columns that say span, 2.4. So there's a 2.7 here, one across is a 2.5, one across is a 2.8, one across is a 2.5. The rafter spacing, so that means how often you have rafters along your room, will determine the sizing, of your rafters. So you need to decide what makes sense in terms of the design of your building, how it looks, like you have options here. So let's say we put rafters every 600 millimeters, which is a common thing. We go into the column of 600 and we go read down, span 2.5, cuts it, and then we read across. So we need rafters that are 140 millimeters times 45. So that would be that's a good size, But you could also choose, I don't want rafters so often, but I want them a little bit chunkier. So you could go, I want them every 1200 millimeters. So then you would go into the column to the right there, 500, read across, and then your rafters would have to be 190 by 45. So again, it's up to you to decide how do you want to size these timbers so that it makes sense for your design. And also you can do cost comparison for the timber. Maybe a certain size timber a little, less often is more cost effective than the other size timber more often. Again, in example 2, we had a span of 1.2 meters. So that is a very short span. You can even put them in at 1200 centers or 900 intervals, and you just work with the smallest timber. So 90-45, that's easy, And then the spans for the other example with A and B, we again had a short span and a longer span. And up to you. I would probably make them look the same. So you need to size them for the longer span, which I think was 3 meters. And again, you would be reading down and seeing the closest thing to 3 meters. So maybe the 3.3 here at every 600 millimeters would be good. And you read across and you see that you need timbers that are 190 times 45. And again, the associated letters to the right are the types of fixing that you require to fix the rafters. So you can read that out of this table as well. And then one more thing that you have in the roof. So just to recap, here you see the ridge beam, you see the rafters, and then you have these other pieces of timber that go the other direction again. So like at a right angle. And they are called purlins, and they are fixing for your roofing materials. So here you actually see why it is important to understand, the length between the rafters is translated into the span that the purlins have to span. So if you have rafters more often, the span of the purlin is smaller. If the rafters are spaced out more, the purlins have to span bigger distances, and that will affect the sizing of your purlin. So let's say you place your rafters every 600 millimeters, here down here, or every 900 millimeters, you see down here, it will ask you, is your building in a high wind zone or very high wind zone? I would suggest you size this for very high wind zone regardless, unless you know you're in an extra high wind zone, because wind is bound to pick up. So don't skimp on this. And then you can read down, you see, it has to span at least 900, let's say, or 750 or 600. Let's say in our example, we had one that was every 600. You read across and you see that you can get away with quite small pieces of timber, 70 by 45. And it will tell you the amount of fixing. So the T, again, reading that out of the table below will give you the fixing. So we're sometimes dealing with a ridge beam. We're definitely dealing with rafters in any type of roof, and we're dealing with purlins. And all three of these types of timbers will have to be sized. Here, I'm just showing you a couple of other things, especially for the earth buildings, but roof overhangs are good for any type of building because they allow you to fine-tune how much summer sun comes in and so forth. They will also protect your walls from excessive rain. So when you're building roof overhangs, there's a couple of different ways of doing it. And I've put in just diagrams of two options. So either you have a little bit of a chunkier thing, like in the top left here with an outrigger, or you actually build this roof overhang with your purlins. So that just shows you, and if you do it with the purlins, you need to make sure that the purlins are strong enough. So they're just hanging over that edge of the roof and they're cantilevered, but they need to be strong enough to withstand wind forces. And just to show you what I mean with the ceiling diaphragm, often that's done with sheet material, and that can also be done with diagonal sarking. But this is how it's installed, like you put your roof structure down, and then either from the bottom into the ceiling or at some point in the roof structure, you attach the sheet, the plywood sheets, so that the whole roof gets nice and stiff. Sometimes that's done with like a metal strap or a diagonal cross brace. There's different ways of stiffening the roof, but for earthen buildings, it's quite important that it is nice and stiff and that it actually has a ceiling diaphragm. So that's done with sheets. And then your purlins would be attached over top of that sheet material. So one thing that you could pay attention to if you know that you will be using sheet material is that you design. We've already thought about this when we were talking about the floor plan, that you're designing to materials sizes, and the sheets are definitely one of the things that I will keep in mind. So the sheets are 1200, 1.2 meters wide. So if I'm working with sheets, I like to have the rafters every 0.6 meters, so 600, so that a sheet covers two spans of rafters, because then the fixing aligns and everything works out well. It's a little bit of a nuisance if you, let's say, design a building that is just a little bit bigger than, let's say, 4 sheets, because then you have to put in a strip and then you have to put in extra fixing for that and so forth. So really encouraging you to think, look down, look up, and think about material sizes, because sometimes just on a plan, just drawing, it's easy to just make a measurement up, but it would be so much easier to just think about these sizes and then just allow for that in your plan, because it has a knock-on effect during building that can add labor and costs and so forth. And further considerations, when you're designing, is compare the different the size of timbers, price them, compare costs depending on material quantities. Really look at the table and see what kind of fixings you require, because the fixing is definitely are a cost. The roofing material, as I said, often is you know, sheet metal, so corrugated iron. Lightweight roofs are quite cost effective and low maintenance, and they don't introduce so much weight into your building. If you have a heavy roof, you will have to go to the relevant tables in the timber frame standard. So you'll see there's tables for light roofs and there's tables for heavy roofs, and you choose the one that is according to the roofing material that you're choosing. If you're wanting to save costs, like sometimes you will be able to pick up secondhand steel. There's definitely a cost associated with the whole roof construction, so it's good to price all of that. And the other thing that adds cost are the flashings. So your decision on the roof shape will have a knock-on effect into costs. So, you know, if you have a shape like this up here, where the sheets of roofing meet, you have to have a flashing. A flashing is a piece of metal that spans over changes in angles, changes in materials, and so forth. So you have flashings in your roof, you have flashings around your windows, and so forth. And flashings cost money. So maybe a mono-pitched roof has less flashings. You know, maybe you want to save costs, and then that would be a reason to go for a mono-pitched roof. Not saying that you do have to do that, but have a think about it, you know, like when you're designing, because design decisions really affect price. So, you know, people ask me, how much does a two-bedroom earth building cost? Like the answer is like the cost often isn't in the wall system. The cost is in other design decisions, and the roof definitely has an influence on the costs. And yeah, very important that you put gutters on, especially if you have an earthen building. But for any building, you know, it's good to get water away from your facade. You might want to think about a roof, you know, the roof overhangs or verandas. For you, you know, for usability, for shade, and so forth. And the veranda roof also has beams and it also has rafters, so you would have to size those as well. And then you're also looking at the angles, so like the pitch of the roof, how steep it is. Different types of roofing materials will dictate different how flat the roof can be. It's safe to be within about 15 degrees, so that you really have enough flow that the water goes out, that you don't have any leaks. But that translates all the way down, so you need to think about head clearances, especially if you have roof overhangs or verandas. The head clearance and also view out of windows and so forth. So tomorrow we will go more into sections of buildings, and we will really start thinking three-dimensionally and really making sure that, you know, those things work. But already inviting you to start thinking about this when you're drawing or conceptualizing your roof plan now, and inviting you into thinking about the roof plan today. So thinking, you know, what kind of shape of roof do I want? Is there a ridge beam? And then sizing, if you have a ridge beam, the ridge beam, but at least size the rafters and the purlins. And really draw it out, you know, draw it out how often the rafters are, how often the purlins are. So draw a roofing plan, and then you can calculate how many meters of each size timber you will require. And as a bonus, if you feel like it, you could call up a merchant, a timber merchant, and get a price per meter so that you can compare things. So that's the invitation for today. I know it was kind of dense. I hope it was clear enough. And I will just circle over to the questions and see how you're going. If you're still here, well done. Yeah, drop me some questions if you have them right now, or otherwise go and digest it a little bit, and you can ask in the group later on. I'll be there. Just tag me, in the things so that it shows up, because I'm having a lot of comments across a couple of different channels. So, Esther, you're making a really good point about the insulation rules and the depth of the wall. I haven't gone into this, but you don't necessarily have to put the insulation just into the layer of the purlins. You can also put insulation between rafters. So depending on where you are and what kind of insulation material you're using, that might be an additional thing you want to look at when you're sizing timber, especially with these smaller buildings, because you could theoretically get away with quite small timbers, but you might have to beef that up, to have enough space to incorporate insulation material. So that is a really good point. It's not relevant for all the places, and it's just something to consider for people in temperate climates. Then there was a long comment that probably I will read later on, because it says, sorry, I didn't realize it was live. Someone was saying, I can't see what column you're showing. Yeah, I am realizing that you guys probably don't see my cursor, which is really annoying. I would suggest that you look at the standard, and the column is the line, top to bottom. See if you can work it out, and if you don't, take a little screenshot and ask me, and I'll clarify it later on. Will we cover insulation materials in the roof? No, we don't. There's, you do have to insulate the roof. You will have to allow for enough space for insulation in the roof, and there's different options for insulating the roof. Typically, we like working with wool. In some countries, you get hemp insulation. Maybe those options are too expensive, and you go to like a conventional insulation material. If you go to something like straw bale, you obviously have to allow the thickness of that. So it is definitely something that needs to flow into the consideration when you're sizing the timbers. And it's always a balancing thing, So like maybe you want to stay within a certain height, certain weight, and then you will compromise on the material you use for insulation. Maybe you have space to work with natural materials, and then you just have to allow for that thing. If you have concrete questions about insulation materials, bring them up in the group. I'm happy to talk about it. Is there a minimum measurement for the overhang of a roof when it's earth brick? Yes, there is, and it's in the earth building standards. There is the eaves requirement. So you go and have a look, and it depends on your location. So it depends if you're in a high wind zone or in a medium wind zone, and it depends how tall your walls are. And you can, out of that, you can read, it's sort of a ratio. It depends on your exposure, like the results of your durability tests of your earthen material, and the wall height. So it's a formula, but the minimum overhang, I think, is 600, and realistically, they're 900 or something like that, unless you're in an exposed situation where you would go to a veranda or something like that. Yeah, Terralana wool insulation in Christchurch are awesome. So the wool insulation and the earth especially they are synergistic. They have similar qualities of breathability and how they buffer humidity. So they go together really well. I love Terralana or any other wool insulation. Okay, so I think there's no more questions coming in. You can keep them coming in the group. I look forward to seeing what you come up with, at least as an initial concept for your roof. And yeah, we can totally develop this together once you have a sketch. And if you have questions regarding the loaded dimension or different choices for timbers, sing out and we'll discuss it in the group. Okay, wonderful people. That brings us to the end of today, and then we'll see each other again tomorrow for more constructive details. Have a good day.